Welcome, focused learners, to the explainer that is going to completely transform how you approach your Cambridge computer science papers. Whether you are tackling syllabus 0417, 0478, 2210, or 9618, you are in the exact right place. Look, we all know the exam hall can feel like a high-stakes arena. I want you to think of this session like you're a game designer, and your ultimate goal is to level up your answers so that every single paragraph you write unlocks new marks. Today, we are diving deep into a topic that trips up thousands of students every single year: hexadecimal representation. But we aren't just going to read textbook definitions to you. Absolutely not. We are going to transform this topic from a dry, memorized vocabulary word into a dynamic, high-scoring exam strategy. I want you to picture two typical students sitting in the exam hall right now. Let's call them Alex and Sam. Alex is the overpreparer. When Alex sees a question on hexadecimal, they overload their answer with raw computer science facts, just a massive chaotic brain dump with zero actual analysis. On the other hand, we have Sam. Sam rushes. Sam panics under the time pressure, glances at the command word, totally ignores it, and gives a safe, generic response that entirely misses the specific requirements of the question. I've looked at thousands of past papers, and my red pen has crossed out so many of these types of answers. Both students lose easily avoidable marks. Today, we are going to make absolutely sure you are neither Alex nor Sam. We're going to build your computer science success blueprint. Let's get started. Here is our roadmap for today's session. We'll start with real-world hooks, move into the 3 layers of learning, and then critically unpack the difference between describe versus explain. Next, we'll look at where students slip up, introduce the correction strategy, and finally, finish up with a 4-question check to test your ultimate exam readiness.
Section 1. Real-world hooks. Because in Cambridge exams, context is literally everything.
In classroom teaching, and in your own late-night revision sessions, the topic of hexadecimal representation absolutely must be approached as part of a connected computer science structure. It cannot be an isolated, lonely definition floating in space. A strong answer and a strong understanding begins in the real world. So I want to pose a challenge to you right now. Think about it. What digital problem does hexadecimal actually solve? Before we even begin to define the terminology or write out base 16 conversion tables on the whiteboard, you need to understand its purpose. Why did computer scientists invent it? What kind of data or device is involved here? What practical consequence does using hexadecimal have for a programmer, a system, or a massive global organization? Cambridge examiners know for a fact that students who only memorize a vocabulary list fall apart the second the exam question introduces an unfamiliar scenario. But students who understand the reason a concept exists, those are the ones who can adapt their knowledge to absolutely any question thrown their way.
And this brilliantly illustrates that exact point. We are talking about the mobile phones in your pocket, the HTML color codes on websites and media handling, MAC addresses in databases and network routing, the assembly code in robotics and automated systems, and the encryption keys in secure online activity. Hexadecimal is the backbone of these everyday technologies. Real-world transfer matters immensely because it converts raw memory into actual usefulness. When you repeatedly connect hexadecimal to familiar technology, you remember not just the label, but the fundamental reason the concept exists. It's to make long strings of binary easier for humans to read, write, and debug. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's look back at our 2 students. If Alex gets a question on HTML color codes, Alex just lists all those bullet points you see right now, completely ignoring the specific question. Sam forgets they even exist and just writes it uses base 16. Neither of them is hitting the assessment objectives, or AOs, that Cambridge requires. To hit those AOs, you have to layer your knowledge.
That brings us to Section 2, the 3 layers of learning. This is how top-tier students actually build their understanding. The crucial point here is understanding this exact sequence. Step 1 is the simple explanation using everyday language. This is where you just wrap your head around the idea intuitively. Step 2 is the technical vocabulary. This is where we bring in the correct subject terms, words like MAC address, IPv6, assembly language, memory dumps. But here is where the tragedy happens in the exam hall. Most students stop at Step 2. They think they know a topic until they hit Step 3, the exam explanation. Step 3 is where the idea is shaped into a structured, logical response that actually scores marks under strict time pressure. How do we bridge the gap between Step 2 and Step 3? We use the PEAL framework. That stands for point, evidence, explanation, and link. If you want to unlock those top-tier marks, you make your point, you provide evidence using that technical vocabulary, you explain how it works, and you link it back to the specific scenario in the question. Many avoidable losses of marks happen because candidates recognize a familiar word, panic, and try to jump straight to a Step 3 conclusion without securing the foundational peel structure. They end up answering a completely different question from the one that was actually set.
Moving on to Section 3, Describing versus Explaining. This is where we decode those tricky command words.
A highly useful discipline for hexadecimal representation and really any computer science topic is to strictly separate description from explanation. You have to decode the command word. Description tells what the device, process, or method is. It's just identifying things. Explanation tells how it works and why it matters. Examiners usually expect both if the command word is explain. Let's look at our friend Sam. The question says, explain why hexadecimal is used to represent MAC addresses. Sam writes, hexadecimal is a base 16 system that uses numbers and letters. Sounds safe, right? But the examiner grades it as incredibly shallow. Sam gave a description, not an explanation. You might get 1 mark for identifying, but you lose all the analysis marks. On the flip side, what does Alex do? Alex writes, it's faster for computers to read and it takes up less space on the hard drive and it helps debug code. Massive red marks everywhere. Alex jumped purely into a chaotic explanation without clearly naming and describing the concept first. And worse, Alex included incorrect facts. Computers process binary, not hex, so it isn't faster for the machine. You need the what, followed immediately by the accurate how and why, structured perfectly through that peel framework.
And this brilliantly illustrates why those foundational concepts matter. The theoretical foundations of hexadecimal representation often depend on understanding important distinctions and concept boundaries. For example, memory versus storage. You absolutely cannot mix these up. Memory, like RAM, is temporary data holding. Storage, like a hard drive, is permanent data retention. Other examples include distinguishing between data versus information, or a compiler versus an interpreter. You must be trained to see these contrasts quickly because they often control the whole trajectory of your answer. If a question asks about hexadecimal being used in memory dumps, which is when the contents of RAM are printed to the screen for a programmer to debug, and you start explaining permanent storage drives and how much space a file takes up, you've completely derailed your entire answer. Your computer science reasoning becomes vastly stronger once these boundaries are clearly defined in your mind.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's get into Section 4, where students slip up. This is our interactive workshop segment. This table right here is exactly where marks vanish in the Cambridge exams. I want to run a quick drill with you. Challenge number 1 is a data scan. Look at this table and extract the core trend. You have a few seconds. Do you see it? The core trend is that a lack of depth and a lack of context equals a loss of marks. Trap number 1, stating an advantage with no reason. You say hexadecimal is shorter, but you don't explain that it's shorter for humans to read, write, and debug, which reduces transcription errors. Result? Lost marks for lacking analytical depth. Trap number 2, identifying a device without justification. You state a router uses MAC addresses, but don't explain why it's represented in hexadecimal for the network administrator. Result? Graded as shallow. Now for challenge number 2, find the flaw. Imagine a student writes this paragraph. Hexadecimal is used in MAC addresses. This is because hexadecimal takes up less memory in the computer's RAM, making the network faster. Spot the flaw? The examiner's commentary would read, candidate incorrectly states hexadecimal saves memory. Data is always stored in binary and RAM. Hexadecimal is purely for human readability. If you can spot these flaws, you are already leveling up.
I want to anchor that last trap with a direct, unavoidable rule from the examiner reports. Generic responses rarely gain full marks. Specificity is everything. If the Cambridge exam prompt sets a scenario in a school, an office, an industrial system, a retail environment, or a secure network, your answer absolutely must stay inside that context. Let's do challenge 3, speed writing. If the exam sets a prompt about a retail environment and asks how hexadecimal might be used when checking for barcode errors, you can't just define hexadecimal. You have to write a peel paragraph. Point: hexadecimal is used to display the ASCII values of the barcode characters. Evidence: when a barcode scanner fails, the raw data can be dumped to a screen. Explanation: the technician can read the hexadecimal values much easier than long strings of binary to spot where the error occurred. link. This allows the retail environment to quickly fix the scanner and keep the checkout lines moving. Adapt to survive. A generic answer gets generic grades.
Section 5, the correction strategy. This is the ultimate blueprint to fix those errors.
Here is your technical sequence, your complete computer science answering system for tackling any process-based question. Step 1. Identify the demand. This is rule number 1 of our blueprint, command word decoding. Is it asking you to state, describe, explain, or evaluate? Step 2. Classify the correct concept. Don't confuse memory with storage. Step 3. Explain the sequence step by step. This is rule number 2, Peel framework application. In exam writing, clarity of sequence matters deeply. Avoid jumping forwards and backwards in a process. It is usually better to explain the mechanism first and then state the consequence. Step 4. Connect back to the context. Check whether your answer actually addresses the school, the database, or the robotics system mentioned in the prompt. And overlying all of this is rule number 3, the time management matrix. Don't spend 10 minutes writing a huge paragraph for a 2-mark state question, and don't spend 30 seconds on a 6-mark explain question. This logical structure produces drastically clearer answers than Alex's chaotic brain dumps or Sam's rushed panics.
So how do we practice this system before the exam? A high-quality revision cycle for hexadecimal representation involves these 3 passes. Pass 1 is where you secure your definitions and key contrasts. You nail down the difference between base 2, base 10, and base 16. Pass 2 is where you rehearse worked explanations. You practice drawing diagrams, reviewing truth tables, or writing out those perfect Peel paragraphs from memory dumps and MAC addresses. But Pass 3 is where the absolute magic happens. Pass 3 focuses entirely on adaptability. You change the context, you force yourself to justify a choice in a completely new scenario. One massive reason students find this topic difficult is that surface features distract from the real idea. They fixate on a tricky new device name in the prompt or a weird keyword they haven't seen, and they completely ignore the deeper process they already know. By practicing Pass 3, you ensure that a shiny new contact won't distract you from the core mechanism. You see through the matrix. Section 6, the 4-question exam check. This is your final self-assessment. When you are revising hexadecimal, or frankly any complex computer science concept, ask yourself these 4 questions. 1. What is it? It's a base 16 number system using 0 to 9 and A to F. 2. How does it work? It groups 4 binary bits, a nibble, into one single hexadecimal character. 3. Where is it used? It's used in MAC addresses, IPv6, HTML color codes, and memory dumps. 4. Why is it better or worse than an alternative in that specific situation? It is significantly better than binary for humans because it is shorter, making it much easier to read, write, and debug without making transcription errors. However, it is not better for the computer itself because computers only process binary logic gates. It is that simple, yet incredibly rigorous. I challenge you to answer these 4 prompts aloud for any topic you are struggling with. If a concept can be paraphrased accurately aloud just like I did, it is far more likely to survive the stress of an exam hall. If you can answer these 4 logically, the topic is ready for examination use. If you stumble, if you sound vague, or if you can't think of an alternative to compare it to, then another cycle of reading, explanation, and recall is absolutely needed. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. So I will leave you with this final provocative thought. Can you explain the core mechanism of hexadecimal aloud right now without relying on memorized wording? Don't just regurgitate a textbook. Explain it like you were teaching a friend. Take control, level up your answers, and master the exam. See you next time.